This video aims to inform on and illustrate the goals, design process, fabrication and analysis for the Trinity University FSAE Senior Design Project. The primary objective of this project was to design a chassis suitable for use in the Formula Society of Automotive Engineers competition, meaning the chassis needed to adhere to all FSAE regulations and accommodate major vehicle subsystems. The approach was to fabricate the design chassis as near as possible to the specifications, to develop a finite element model of the chassis, and to validate simulated results with physical testing. The frame was designed in three subsections: the cockpit, the front, and the rear. Per FSAE regulations, the cockpit must accommodate a man in the 95th height percentile, and a line extended from the top of the main roll hoop to the top of the front roll hoop may not come within 2 inches of the driver's head. The front section of the chassis was designed to accommodate a direct-acting double wishbone suspension with short, long A-arms, by including parallel bars to act as hardpoints, and with a nose that interfaces with the chosen impact attenuator design. The rear section was sized for a Drexler differential and an engine which was sourced from a Yamaha Phaser snowmobile. A digital model of the frame was built first using the Creo Parametric Advanced Framework extension to nest frame members of the specified diameter and wall thickness over the wire frame load parts that constituted the frame design. Then, a joining function was used to form a combination of miter joints and fishmouth notches to join the frame members. Upon completion of the computer model, individual part files with dimensions were printed for each frame member. These parts were cut from pieces of steel tubing to the correct length and end angles before being welded together. Operational and crash loads were simulated with Creo to assess whether or not the chassis could adequately distribute driving forces through proper load paths and protect the driver in crash scenarios. It was not possible to physically test the operational and crash load cases without either fully assembling the vehicle or damaging the chassis. Instead, the validity of the computer results was assessed by simulating a simpler load case that could be physically tested. A known load was applied to the front roll hoop with strain gauges attached to another member. The measured strain was recorded with a data acquisition unit to be compared to the simulated test. The simulated strain results proved very sensitive to the exact measurement position. The colors around the measurement area, boxed in orange, represent values between 20 and 50 microstrain under a 1,000 pound load. The actual strain, measured with the strain gauges, was recorded at about 44 microstrain under the same load. Even at our highest estimates of uncertainty, at 20%, the measurement still falls mostly within the simulated range. Another way to assess the quality of the chassis design is torsional rigidity, as it is an automotive standard indicative of vehicle handling performance. Essentially, the more torsional stiffness a frame has, the more it keeps its intended shape during loading, so the suspension can act as it is designed. Creo was used to simulate the design's torsional rigidity. The group constructed a testing rig with a clawed lever arm that attached near the suspension mounting points and mimicked the force applied in the simulated test. The rearmost lateral frame member was clamped to the table to emulate the constraints placed in the simulation. A known load was then applied to the lever arm, and the degrees of rotation were measured using a precision inclinometer. The torsional results were compared to a handful of other FSAE teams and fell somewhere in the middle. Some teams report high torsional rigidities that likely require a heavier chassis, which decreases overall performance. The disparity between the simulated and measured values can be attributed in part to weld imperfections and some rotation of the rear member during physical testing, where it was perfectly constrained in simulation. We would like to thank our group advisors Dr. Jack Leifer and Dr. Michael Enright, our course supervisor Dr. Farzan Aminian, Barbara Pierce for her generous donation, our resident technicians Manuel Garza and Ernest Romo, as well as the rest of the Trinity faculty and staff who helped us both on this project and in our time at Trinity.